Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study some of the problems and how to apply the expressions of moment of inertia of various sections, such as rectangular sections, circular sections, and a hollow rectangular section and a hollow circular section, and how to apply those expressions. And going to learn through problems. In previous sessions, we have learned what is moment of inertia and what is the expression, what is the simple definition for moment of inertia. Mathematically is a moment of inertia I equal to sigma times AR square, where small a is area of the section and R is the distance, corresponding distance from the line of section. R1 and R2 and R3 are corresponding distances of elements from the line about which the moment of inertia is going to be found or determined. And A1 and A2 and A3 are area of the small elements. The meaning of this is that the moment of inertia, the arbitrary shaped plane area is converted into small elements having areas A1, A2, A3 and so on. And the areas having center of gravity or centroid. The distance from centroid to where the line of action, where the line about which the moment of inertia is going to be calculated, those distances are known as this R1, R2, R3 and so on. Okay, and this moment of inertia equal to A1 R1 square plus A2 R2 square plus A3 R3 square and so on. So this is then I equal to sigma times the sigma AR square. This I equal to here I equal to AIR square. I equal to 1 to n. This is the moment of inertia of the total plane area. So what about the unit of moment of inertia? Here the moment of inertia is of area moment of inertia. Here it is. The unit for area moment of inertia is mm for 4 or meters power 4. So broadly, the moment of inertia is two types. One is mass moment of inertia, another one is area moment of inertia. The mass moment of inertia is applicable to calculate the moment of inertia, where in design of components or design of the structures, mass moment of inertia is highly useful. Whereas here, the area moment of inertia is useful where we have to calculate where we have to calculate maximum moment, bending stress, modulus of rigidity, modulus of velocity, torque, shear stress, etc. are going to be calculated. Then where this area moment of inertia is highly required. Now let us begin with what we have done. We are going to solve. Suppose if we consider certain things as we have already solved. Suppose for a solid section, the expression for area moment of inertia is BdQ by 12, where Ixx equal to BdQ by 12. Here, these axis passing, these xx and yy are passing through the CG, the centroid or center of gravity of the section. So, if it is in that case, that is Ixx, the axis xx and yy are passing through CG. That is BdQ by 12, and what about Iyy about vertical axis? That is dBq by 12. There B is the width and D is the depth. Now B is the width and D is the depth. Now about Yy, it comes parallel to that. Yy is the dBq by 12, and here Ixx parallel is the parameter is the B, begins with the B, and perpendicular it is hitting the D. That means here to remember what is the BdQ by 12 and dBq by 12. So, suppose if the area, find the moment of inertia of the rectangular section, here 30 mm and 40 mm deep about x axis and y axis are given here. You have to calculate. We are already solved. Suppose if the moment of inertia, if the dimensions of the rectangular section, the depth is given here as 20 millimeters. And the width is given as 40 millimeters. Then what is the moment of inertia about the axis which is passing through centroid? This is the x-axis and y-axis are passing through centroid. Then what about I-x here? I-x equal to, as we have solved, we consider D equal to 20 millimeters and whereas B equal to 40 millimeters. Here the width is greater than or larger value than a depth. So what about I-axis here? I-axis equal to B dq by 12. What about the B? B value is 40 millimeters. What is the D? What about D value? That is 20 millimeter power 3 by 12. Then we'll get the answer that is in terms of millimeter power 4. The value is obtained. So okay, the value is obtained I-x here. Thus we can calculate. Now what about I-y? I-y value comes I-y equal to, what about I-y for this problem? I-y equal to db power 3 by 12. That is, what is D here? 20 times B, 40 power 3 by 12. So the value will obtain here in the units of mm 4. If you understand here, the value of I-x is greater than the value of I-y. Why here? Why so? Because here the width is larger in value. Here B dq by 12, D is the 20. The value of I-x, the value of I-x is smaller than I-y. Why? The D is smaller than B or B is greater than D. So I-y db cube to D power B cube. B is the 40 cube by 12. That's why I-x is smaller in comparison to I-y. Whereas if we consider the problem of this 30 and 40 millimeters, this is the 40 millimeters db cube. Here in this case study, I-x and I-y. Okay. For this, if we consider this 30 millimeters and 40 millimeters, B equal to 30 millimeters and D equal to 40 millimeters. Then in this case, I-x is greater than I-y because the D is larger than B. Why? The I-x value here, the I-x that is B dq by 12 is greater than D bq by 12 because D is the depth is in larger value. That's why D bq by 12 is larger than B dq by 12 is larger than the D bq by 12. Now this is for rectangular section. For a hollow rectangular section, if the dimensions were given for hollow rectangular section as, suppose if you consider the hollow rectangular section for this, I'm considering here the D and B are 40 and 30, and if you consider here it is 20 and here it is 15. That is considered as a D1 and here it is B1. So D equal to, what is the D here? It is 40 millimeters and B equal to 30 millimeters. Now D is 40 millimeters, B equal to 30 millimeters and D1 20, B1 is 15 millimeters. Then what about I-x? We want a hollow circular. This is a shaded zone. We need the shaded zone of the section. This is the shaded zone. What about the shaded zone? If you remove it, if you subtract, this zone should be removed. Then the shape of the shape will be obtained here. We want hatching portions moment of inertia. For that case, how to make it? This B dq by 12 here. Yeah, how to go through it? Now I-x equal to, what is I-x equal to? I-x equal to B capital B dq by 12 minus B1 D1 q by 12. We have to subtract. Then only this hatching portion can be calculated. What about here the B dq by 12? That is 30 into 40 q by 12 minus, what about B1 D1? What is the B1 here? 15. What is D1? 20 q by 12. So this is I-x value. The Ixx will be obtained in terms of millimeter power 4. Next, what about Iyy? This Iyy is equal to, what is Iyy? That is dB cube by 12 minus d1 b1 cube by 12. What is d here? The d is here, it is 40 into 30 cube by 12 minus, what is d1 and b1? Substitute in this expression. What is d1? 20 and b1 15 cube by 12. This is Iyy. Now you can understand which value the moment of inertia parallel to x-axis, that is central Ixx is greater or smaller. Yes, here the xx value for this case is larger than the Iyy. Okay, why? Because the depth of d is greater than b and d1 is greater than b1. So thus we have to solve the moment of inertia as parallel to x-axis, parallel to y-axis. Okay, now suppose as we have calculated this Ixx, we already solved in previous session for hollow rectangular section. This Ixx equal to bd cube by 12 minus b1 d1 cube by 12. This is the hatching portion. This portion, colored portion, is required moment of inertia. Now Iyy. Why? Because here it is symmetrical about both xx and y axis. Suppose if we consider some of the sections, we'll consider more detail. If we consider the circular section, this is the circular section, this is xx axis, and here it is the y. Then Ixx equal to, which is having the diameter d. What about moment of inertia? Ixx equal to pi d power 4 by 64, and Iyy equal to pi d power 4 by 64, and here then Ixx equal to Iyy, that equal to pi d power 4 by 64. And we studied if we apply, we want Izz, then Izz equal to, according to the concept of perpendicular axis theorem, Izz equal to Ixx plus Iyy. And then substitute here pi d power 4 by 64 plus pi d power 4 by 64. That equal to 2 times pi d power 4 by 64. And then Izz equal to pi d power 4 by 32. So the moment of inertia, this Izz is known as the polar moment of inertia. It comes with studying that Izz equal to polar moment of inertia about perpendicular axis. Normal to the surface of the circle plane, that is polar moment of inertia. Now, if we want to calculate, in this case, if we compare the values, the expressions of circular section with rectangular section, circular sections, and the moment of inertia calculation, circular section with the rectangular section, if you calculate, whereas for circular section, the comparison between circular sections, moment of inertia, MOI, and rectangular section, moment of inertia values. Here in this case, Ixx equal to Iyy, whereas here Ixx is not equal to Iyy. And circular section depends upon only one parameter, that is the diameter or radius. Whereas the rectangular section depends on moment of inertia, it depends on B and D. Okay, if D is the only parameter here, Ixx equal to Iyy. So here again, because about xx axis same as y axis, because it's only single parameter. Whereas for rectangular section, Ixx always can be greater than Iyy, or Ixx can be less than Iyy. It depends upon what is the D? If Ixx is greater than Iyy when D is greater than B. If Ixx is less than, that means if D is less than B, Ixx is less than Iyy. Okay, whereas in this case, it is only single parameter, always there is nothing, D is greater than B or not, it is only one parameter D. Now, the moment of inertia for circular section, that is Ixx equal to Iyy, that equal to pi d power 4 by 64. Whereas here, for rectangular section is having the depth D and width B, and here the axis Ixx and Iyy. What about Ixx and Iyy here? The Ixx equal to BDQ by 12, and whereas Iyy equal to dBq by 12. Now, the unit for both circular section moment of inertia and rectangular section moment of inertia is both same, that is millimeter per 4 or meter per 4. Whereas for rectangular section it is same, millimeter per 4 or meters per 4. So this is the comparison between the circular section and rectangular sections moment of inertia. Alright, now here one more important is that so far you have studied only the moment of inertia which is passing through the centroidal sections. Alright, which is passing through only the centroidal sections of both circular section and rectangular section, hollow circular section and hollow rectangular section. Now suppose if you want to find out the moment of inertia about some line, that is PQ. Here it is XX and here it is YY. Similarly, some reference axis, it is QRS. So this is easy. How to find out the moment of inertia of this rectangular section having a width B and a depth D. So we already calculated, we already derived expressions for CG parallel to x-axis, that is Ixx. This x-axis is passing through the centroid, that's why I make it as Igx, that is BDQ by 12. Now Igy equal to whatever Igy, that is dBq by 12. And how to find out this type of things? We want to find out the moment of inertia of this rectangular section about the line PQ. Then we have to go for parallel axis theorem. Parallel axis theorem. This theorem says that, parallel axis theorem says that about an axis moment of inertia, that IPQ equal to the moment of the sum of the sections parallel axis, that about centroid Igx plus total area of the section times the distance between the center of gravity of the section to the about axis, that is suppose bar y. Now how to find out here? That is a by bar y square, that is IPQ. What is here? The parallel axis theorem about the line IPQ equal to what is Igx here? The Igx we calculated BDQ by 12 plus whatever the area B times D. What about bar y? The bar y, if you want it, suppose if you consider it is x, small y, this distance is d by 2. So then what will happen? Bar y equal to y plus d by 2 whole square. So this is IPQ, means moment of inertia about the line PQ. Then this is the expression we derived. Similarly, the same concept methodology is applicable if you want to find out the moment of inertia about RS. Then how to calculate the moment of inertia about RS? Yes, let us begin. IRS equal to Igy, because center of gravity parallel to y-axis times area times Here the distance from here to here, it is bar x whole square. This bar x, here it is, the distance is small x. Then what will happen here? Whatever IGY, IRS equal to IGY. IGY means that is the dBq by 12. dBq by 12 plus whatever the area, B into D, whatever bar x, the bar x equal to small x plus B by 2 whole square. So this is the expression for IRS equal to dBq by 12. dBq by 12 plus BD times x plus B by 2 whole square. This IRS is the moment of inertia about the axis RS, and IPQ is the moment of inertia about the line PQ. Thus, we have to calculate the moment of inertia of the simple figures about some particular sum about the lines. Here, the theorem used, here it is, the parallel axis theorem is highly useful for such calculations. Alright, now let us begin for next one. Suppose if you want to find out the moment of inertia, okay, of some T section, simple section we are going to take it. Simple section, that is a T section. It is symmetrical about axis Y. Okay, it is not symmetrical, it is one line symmetry. Now this T is having here section 1, and it is section 2. Now the width of this is the B1, and here it is D1, and what about it is B2, and here it is D2. Okay, now there are two sections. Whatever individual centroidal, whatever IG here, IGX1, this IGX1 equal to B1 D1 Q by 12. IGX2, there are two sections parallel to x-axis, individual centroidal. Okay, IGX2 equal to B2 D2 Q by 12. The next IGY1, because parallel to vertical axis, this IGY1, that is D1 B1 Q by 12. IGY2, that is D2 B2 Q by 12. We have to find out the moment of inertia about the centroidal axis of this T section. First of all, what to be found? We have to find out bar x and bar y. Here the bar x is already symmetrical about axis y, so it is passing through the centroidal axis, so bar x equal to 0. What about bar y? It is a vertical distance. How to find out bar y? This is a centroidal distance. Bar y equal to a1 y1 plus a2 y2 by a1 plus a2. What about a1 here? This a1 equal to b1 d1. What about y1? The y1, consider the reference axis. This is the reference axis. What is the y1? y1 equal to d2 plus d1 by 2. What about a2? a2 is b2 d2 y2. What is the y2? Is d2 by 2 by a1 plus a2 b1 d1 plus b2 d2. We'll get this bar y value. Okay, in some quantity, if we give some quantities here, the quantity of b1 d1 b2 d2, if we know, if we substitute here, then we'll get bar y. Now how to find out? After calculating the bar y distance, suppose the bar y is at a distance of some axis. Here it is the bar y, the y. Now what is the moment of inertia about the centroidal axis GG of this section? Now IGG equal to I section the parallel to section 1 plus I section 2. What about I section 1? That is about the axis IG x1. Okay, IG x1 plus A1 times IG x1. We want vertical distances. The vertical distances, yes, IG x1 plus A1 times, what happened? Vertical distance, that is here from this point to this is y1. Okay, so that is y bar or y1 minus, you can make it y bar minus, no problem, y bar minus y1 whole square. Next, what about I2? IG x2 plus A2 times y bar minus y2 whole square. Now this is another one, this is y2. Whatever here IG x1, here remember this gx1 is parallel to x-axis. What is IG x1 here? b1 d1 cube by 12. It is parallel to x-axis, and a1 times area of the section 1 bar y. This bar y we have calculated, bar y minus y1, distance from center of section 1 to reference axis, y bar minus y1 whole square, plus IG x2. This IG x2 times, what about IG x1 here? IG x1 is b1 d1 cube by 12. What about IG x2? That is IG x2 is b2 d2 cube by 12. This b2 d2 cube by 12 plus b2 d2 times bar y bar minus y2 whole square. Thus, we'll calculate about the centroidal axis of moment of inertia by considering here, we consider what we considered here. We consider it as a, it is symmetric T section we considered, and we use parallel axis theorem. By using parallel axis theorem, we calculated the moment of inertia of a T section. It is single line of symmetry section. Okay. Now, thus this in this the methodology here it is the manner we have to calculate various sections of moment of inertias of the various sections. All right. Now we are going to consider one more, that is the circular section. Suppose how to find out the moment of inertia of a circular section. Yes, how to calculate the moment of inertia of a circular section. Now, by using the parallel axis theorem, about it is the PQ, the axis is passing through. I'm considering here x-axis, it is having the diameter d. Diameter is d. The distance from IXX to PQ is, yeah, directly, it is, you can consider it as a bar y, or it is the y1. Now here it is some y. What about here to the diameter d? We want IPQ. IPQ equal to IGX1 plus area of the circle A times. Here the distance from, that is from here reference axis to here, that is bar y I already considered. Otherwise is the bar y whole square. What about IGX1? The IGX1 equal to IGX1. IGX1 equal to pi d power 4 by 64. Now substitute here pi d power 4 by 64. What about area? Pi d square by 4, or pi r square times bar y square. That is IPQ. So this is for circular section moment of inertia about the line PQ by considering diameter d. All right. Suppose if you have to consider moment of inertia of I sections. This I section is symmetrical about, it is exactly having both width and depth all are same. So it is symmetrical about both axis X and axis Y. It is the two lines of symmetrical section, I section. Okay, then how to calculate for such type of sections moment of inertia? Okay, it is symmetry, then directly centroid can be calculated, the CG can be calculated directly located. If we know direct location of the CG, then what happens? This IXX, what will be the centroidal axis of IXX, moment of inertia, IXX and IYY for such sections. Now, here in this case, here it is having that 100 millimeters. Okay, flange 1, and the thickness is 10 millimeters. Similarly, bottom flange is having, the width of the bottom flange is 100 millimeters and the thickness is 10 millimeters. Okay, distance between these two, again you consider 100 millimeters and 10 millimeters. For such type of sections, how to calculate? Here the location of the centroid is directly we can locate it, that is the total distance by 2, half of the vertical distance by 2 and horizontal distance by 2, that is the location of the CG. What is the location of the CG? Here it is, this is 10 plus 100 plus 10, that is 120 by 2, that is the 60 from reference axis. Here it is 60 millimeters. Whatever the location from here, that is the distance, that is 100 by 2, that is 50 millimeters. So bar X comma bar Y equal to 50 millimeters comma, that is on 60 millimeters. Here that section is symmetrical about both horizontal and vertical. Location of the centroid, this IXX and IYY is passing to that. Now consider the various sections. Yes, this section 2 and this section 3. For such type of sections, how to calculate the moment of inertia? Yes, you try for it by using parallel axis theorem. Otherwise, I'm going to explain in the next session. Okay, and how to apply and what are the parameters involved in using parallel axis theorem for such type of two lines of symmetrical sections. In previous slide, we have studied that whatever T section, the T section is the single line of symmetry, vertical about vertical axis, symmetrical about vertical axis. That's why we calculated it is not unsymmetrical. What about that? IGXX, that is IXX. Okay, this GG parallel to XX axis, IXX. That's why the formula is here. We did not go for this IG parallel to G about vertical, IGYY. This one, because it is already, this YY axis is passing through centroid of T section. That's why here IGYY is not required. It is already off of the distance, that is B1 by 2. Okay, now in this session we solved purely problems of moment of inertia. We calculated the moment of inertia of solid rectangular section, hollow rectangular section, and solid circular section, and also how to use parallel axis theorem. By using parallel axis theorem, how to calculate moment of inertia of your T section, and also discussed about I section. For such type of sections, how to calculate. Here it is for calculation of IXX, IYY, there will be this expression of parallel axis theorem will be modified. Alright, we're going to solve in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.